Hello, calculus students. In this video, you will begin to learn about the lovely and fascinating subject of indeterminate forms. And of course, new horizons will begin to open for you as your brain rewires itself in response to this earth-shattering information. So why do we care about this subject? Well, you know in calculus, you have to compute limits. In many cases, for instance, derivatives and Riemann integrals are both defined as limits. Now, it turns out that there are some limits that you cannot tell the value of that limit by simply substituting in values for the variable in the function that you're taking the limit of. When that happens, the limit is called an indeterminate form. And it's easiest to understand these from working examples, and so I've written some examples here. Now, what we're aiming toward is a method for solving these limits, and that's called L'Hopital's rule here. So that's what we're going to get to, but first we want to examine a few examples of these types of limits and understand where the terminology comes from and what the expressions mean. In particular, you may be looking at some of these expressions I've written here: 0 over 0, infinity over infinity, 0 times infinity, 1 to the infinity. And you might think, well, these are not valid algebraic expressions. They don't give me valid, unique, real numbers. And you're absolutely right. These are not valid expressions for real numbers, and that's the whole point. That's why they're called indeterminate forms. Now, these are not intended to represent specific numbers. They are shorthand, this, and this. They are shorthand for a certain type of limit. And then over on the right-hand side, here, 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 and here, I have shown you examples of this type of limit. And there are many other examples too. And there are also other kinds of indeterminate forms. I mean, for instance, infinity minus infinity is an indeterminate form. So let's begin with this example here where I've written 0 over 0. And we're going to look at this specific limit here that I've written on the right. Now this is limit as x goes to 0 of sine x over x. Now I've told you in this case what the answer is. It's 1. But you should know that already. So this is, I'm sort of reminding you, right? This is like a review. You should remember this limit. From calculus 1, this is a calculus 1 thing. So this is calc 1 stuff. But now we're asking the question, but why? But why is it true? Now I claim that you do know, or that you should know on the basis of calculus 1 material, you should know at least 2 methods for coming to this answer here, for figuring this out. But first, I want to look at what you would do just from the most naive perspective and show you why it doesn't work. So what the naive approach would be, it's funny how naive, there's 2 dots over the I. It's I don't know, I guess it's not originally an English word or something. So the naive method would be substitution. And I will caution you from the outset that this won't work. But we're going to show why it doesn't work. So what you would do is you would write limit as x goes to 0 of sine x over x equals, and I'm going to put a question mark over the equals because it won't work. And so this is kind of a questionable thing, and then we'll see that it doesn't work. Well, so what the substitution would be is just substitute in the value. See here, x is approaching. Let me write this a little neater. X is approaching 0. And so I could say, well, let's just try to evaluate the limit by putting in the value to which x approaches, which is 0. And in a lot of cases, for a lot of limits, that works, but not here. It won't always work for you. So this would say sine 0 over 0. And you know sine 0 is 0, so this would be 0 over 0. And I've put a question mark here once again because this isn't really valid. And so here's where my algebraically invalid expression comes from. It comes from this naive attempt to try to figure out the answer by just substituting in the value that x is approaching in that limit. So this is where the 0 over 0 comes from. So what I get out of this, so I get an invalid or undefined, I guess I'll say undefined, so I get an undefined expression. That, of course, is this expression here, 0 over 0. And so what does it mean? What does it mean? I could put question marks after this because I haven't really determined what that means. And so this thing is called, we call this indeterminate. Indeterminate. This is not determinant, you know, the N-A-N-T, like determinant of a matrix. It's indeterminate, something which is undetermined. It has not been determined. Now, let me just briefly say, I'll just write this and then I'll erase it. Why would I say indeterminate? Because see, what this seems to imply, just from the way the word is used, is that it's ambiguous, that it's not. Well, if I say it's not determined, that seems like it could be one way or the other, like it could be more than one different possible value. And that's true. And that's a good way of thinking about it. Because see, what would happen if I take so I'll say compare this to a similar limit. So I'll say compare this to, and I'm going to do a very similar limit. This is just limit as x goes to 0. And then I'm going to write 2 sine x over x. Well, if I do this same thing, this same naive approach, I'm just substituting in values. I would say 2 sine 0 over 0, which is, of course, 2 times 0, because sine 0 is 0 over 0, which is just 0 over 0. Now, so I'm getting the same indeterminate form. See, this indeterminate form here, 0 over 0. I'm getting the same expression here. Now, I know that this value, the correct value, so I'll just write here this correct value, in this case would be 2. That's what the correct value would be if I actually worked out the limit. Now, so what this is kind of telling me is that in this case, with this limit here, this just the sine x over x, somehow the 0 over 0 here is supposed to mean 1. Whereas over here, the 0 over 0 is supposed to mean 2. So it can mean different things, and that's why it's called indeterminate. By just writing the 0 over 0, I have not told you enough information to be able to determine an actual unique, well-defined real number answer for what the limit is. So that's why it's called indeterminate. So this naive method, it won't work. It gives you this thing that could be anything. It could be 2, it could be 1, it could be a million, it could be minus pi, it could be anything. So that won't work. Now, like I mentioned before, you do know a couple of techniques that will work. So I will remind you this. You know at least 2 methods that will work. I'll just say that work because I can't fit the word will here. Now, why am I showing you these? Because these aren't the ones I want to teach you now. This isn't L'Hopital's rule. We'll get to that later. Well, the reason I'm showing you this is I want to motivate L'Hopital's rule. I want you to want another method. And so these methods are no fun. You will hate them. And so the next 10 minutes or whatever it is going to be devoted to convincing you that you don't want to use these methods. So the first method would be I could view the limit as a derivative. How would I do that? It's maybe not immediately obvious how you would do this. Well, you remember the definition of the derivative. So if I have any function, I can write the derivative as f prime of x is limit as h goes to 0 of f of x plus h minus f of x over h. That's the definition of the derivative. And I'll remark that sometimes it's convenient to write the same thing as d dx of f of x or df dx. There's all these different notations. And when I start using a different notation, I don't want you to think it somehow subtly means a different thing. It really means the same thing. I'm going to just take these off for now. So f prime of x equals this. Now this is always true for any f where the derivative is defined. So if this limit is defined, then it's differentiable, and this is the definition of the derivative. This goes back to calculus 1 still. Now, suppose I choose a particular function. So say I choose, and you know what it's going to be because it's the one we're looking at. So we're going to choose f of x to be equal to sine x. And I'm also going to choose a particular value for x. And it's going to be 0. So when I make these choices, what I'm going to get is the derivative. And so now is when I'm going to use that d dx notation. I mean, I could write sine prime, but that doesn't look any good. So I'll write d dx of sine x evaluated at x equals 0. You know what this means, right? The vertical line, and then with the x equals 0 down here means that you find the algebraic expression for the derivative, and then you substitute in 0 for the variable, evaluate it at 0. So this is going to say, so what I'm going to do is I'm just going to take these choices and substitute it into the difference quotient here. So that's going to say limit as h goes to 0. Well, f was sine, so this is sine. X I chose to be 0, so this is 0 plus h minus, and then this is sine of 0. Sometimes I may write sine of 0 like this, and sometimes I may forget and just write sine 0 here. And they mean the same thing, it's just being sloppy or not. I guess since I've written parentheses here, I'll write parentheses here just so it looks the same. And then this is all over h. And then when I substitute this stuff in, of course, evaluate it, 0 plus h, so this is limit as h goes to 0. Well, that's just sine h. See here, I didn't put the parentheses. Maybe I should, because otherwise you'll think it's hyperbolic sine. So let me put sine h here. Sine 0, you know, is 0, and this is just over h. Now this expression here, if I draw a little star here, it means exactly the same thing as what this expression here does. It's just here I've called the variable that's in there h, and here I've called it x. I mean, if this would mean the same thing as if I wrote limit as smiley face goes to 0 of sine of smiley face over smiley face. It doesn't matter what you call the variable. So that's the same thing here. Okay, so what's the point of all of this? Well, what is the derivative of sine? So you recall the derivative of sine is cosine, right? So I'm just going to write this here. So remember, so I'm going to say recall d dx of sine x equals cosine x. So then when I take d dx, when I take the derivative and evaluate it at 0, that's just cosine 0. So, which is what this expression is over here. So this is saying this whole thing is cosine of 0. Well, you know what cosine 0 is. I guess I should put my parentheses here for consistency. You know cosine 0 is 1. And so that is one way to get there. That's one way to tell that this is, I've actually told you the right answer here. Now, my experience is that most students, if I show them this, I say, oh, you know, you can evaluate it by viewing it as a derivative. Their response is something along the lines of, how would I know how to do that? And and so and it's not obvious, is it? I mean, it's why would you think look at this and think immediately, oh well, I can view that as a derivative? And what's even worse than that is that it's something that won't work for every expression of this type. Well, it depends on what you mean of this type. It won't work for every indeterminate form. It won't work for every 0 over 0, but you can't always do this. It's not general. It's not, and so it's not easy to remember how to do it and how to substitute the stuff in. B, it's not going to apply to a lot of the problems you would want to apply it to. So this is bad. This is a bad method. Relatively speaking, is bad because there are better ones, and that's the one we're going to look at ultimately. However, there is one other method that I want to remind you of, which is also not such a good method. And so this is, having erased that, this is method 2, and this is what's called the squeeze theorem. Or sometimes it's called the sandwich theorem. Now what you do in this method is the easiest way to understand is to draw a picture. So I have here the function, and so this is a function I'm going to be looking at. And so this function is my sine x over x. And what I do is then I take two other functions, and I'll call this function here h of x, and I'll choose it in this case to be 1. And then I have another function here, which is going to be, if I can draw this, just a little bit of it here. This is cosine x, if I can just fit it in there. Now, these all come together at this point 0, so at x equals 0. And so now the point is, this idea of squeezing, the point is, and I guess I'll call this, I call this 1 here, I call it h of x. Let me write this in the other order. I'll say this is 1, and in general I'm calling this h of x. This is cosine x, and I'm calling this g of x. So what I'm doing in general is I'm taking the function I want to evaluate, which I'm going to call f of x. Remember last example I called f sine x, so I'm renaming f here. It's different. In this case, it's this quotient, sine x over x. And so what the squeeze theorem says, basically, just in intuitive expression, so if I can squeeze f between g and h, then the limits are the same. I'll say the limits agree, just so I can write fewer words. Now this, of course, is an imprecise way of describing it. I could write it out much more precisely than that, but the point is that you have a function, you want to find what the limit is, you don't know what the limit is just by substituting. And so what you do is you find two other functions which you do know what the limit is. You see here, because the point is, limit as x goes to 0 of, well, h of it, I guess I'll write the g first. G of x, this is equal to limit as x goes to 0 of cosine x, and that, as we saw before, is 1. And it's also true that limit as x goes to 0 of h of x equals limit as x goes to 0 of 1. And that, of course, is 1. It's just a constant. Now, because f is trapped between this, see, you need a hypothesis. You need to be able to say, okay, well, f is between g and h on some interval here, and then it's trapped between those two, and so the limits will be the same. That's kind of the moral of the story. Now, the typical student will maybe be okay with this when it's done in Calculus 1. But later, if you want to apply it, or if you want to have somebody remember it, then they'll be like, how do I remember what to choose for G and H? And it's not fair. and all this kind of thing. Because you have to supply something. See, it's not something where you can just do a particular algorithmic technique. you have to be able to tell what should I call my g, what should I call my h. You have to pull something out of thin air in order to be able to solve this. So this, once again, and the other thing is that what if I can't find a good g and a good h that track the f between it? So this is bad as well. This is also a bad method, relatively speaking, because we have a better method. Okay, so let's now turn to what that better method is. So this is what's called L'Hopital's rule. Now I realize it looks like I've skipped over this stuff here, but what I'm doing is I'm taking this example here and I'm showing you L'Hopital's rule for this example, and then we'll look at the next example and so on and go like that. So I have my examples written out here, and then I have the technique written out over there, and so that's the logic of it. So what L'Hopital's rule, now I've written the hypotheses and the conclusion of L'Hopital's rule over here. So I'm just going to say kind of a much simpler expression of it here. So what L'Hopital's rule lets you do is to evaluate, let's see if I can spell this correctly, evaluate limits in terms of derivatives. Now, this is kind of turning something around from a conceptual perspective, because you know derivatives are limits. So from first principles, you evaluate a derivative by working out a particular limit, namely the limit of that difference quotient. Well, this is turning this around and saying, well, I can work out certain limits by working with derivatives. Now, when I've written L'Hopital's rule over here, you notice I've written that 0 over 0 over there, and that's because the stuff I've written here applies to the case where the indeterminate form that you're looking at is form 0 over 0. So what do I mean by that? So this says whenever, so I mean, not say whenever because there are conditions on it, but if I have a limit which looks like this, limit as x approaches, now I'm just going to say some number c. This number c here is certainly not necessarily the 0 that it was when we were looking at this thing here. It could be n plus, it could also be plus or minus infinity. It need not be, it's what's called an extended real number. But I'm just writing the case here where it lives inside an interval from a to b. So this is a limit as x approaches some number c of a quotient of two functions, f of x over g of x. So if I have a limit that looks like this, then under certain conditions, now that's what all this stuff is, the 1, the 2, and the 3, and all this. So under certain conditions, this limit here is going to be equal to the limit as x goes to c of the quotient of the derivatives, f prime of x over g prime of x. And this is easy to apply. Now let's see how easy to apply, and then we can worry about the details later. So I have room to write it down here because it doesn't take much writing. So for example, it's that first example there, 1. It will turn out that this limit here satisfies those 1, 2, and 3, those conditions, those hypotheses. And so what I'm able to do is I'm able to write that the limit as x goes to 0. In this case, the c is 0. The limit as x goes to 0, let me write this a little more neatly. Limit as x goes to 0 of sine x over x is going to be equal to, so I can take the derivatives in this case because that satisfies those hypotheses there. So I'm going to write d dx of sine x over d dx of just x. And so this is limit as x goes to 0. And now the derivative of the sine is a cosine, you remember, so this is cosine x. The derivative of just x itself is just 1. So this is limit as x goes to 0 of just cosine x, nothing else, and that is 1. And that you can tell it by just substituting. Because it's not an indeterminate form. It's just, it's something where you can substitute the x equals 0 in there directly to tell what the limit is. And so there, in case the limit is 1. Now this was not only was it much easier than those other two methods that I wrote, but it was something that didn't require any ingenuity. It didn't require, it's like this lowers the, it's like your IQ can be 30 points lower and you can still use L'Hopital's rule, whereas you'd have to be 2 standard deviations more intelligent to remember how to write this thing as a derivative or remember how to use the squeeze theorem to do that. So it requires, basically the point of having theorems and techniques and stuff is to let us be as dumb as we can be. Because, that way we don't have to be super clever every time in order to solve a problem. We can do it in a systematic, algorithmic sort of way. Okay, so that's a nice way. So I said the other ways were bad, and I guess I can write here. So this is good. So this is a good method. Now, so far I've just shown you one example, and I've sort of talked to you about what the rule is. I haven't told you much about those hypotheses there, nor have I told you why it's true or anything along those lines. So let me take off this example here, and then I want to look at these. The order in which I'm going to do this is I'm going to look at these other examples a little bit, and then we'll talk a little bit more about the details. So this example 2, this is a limit. Now this is different in some very obvious and notable ways, x over ln x. And I'm telling you that the right answer is infinity. Now there's a good reason, there's many good reasons why this answer had better be infinity. And this is just for your general mathematical education, and I have a captive audience, so I'll spend 30 minutes. No, I'm not going to spend an extra 30 minutes, but I'll spend an extra 30 seconds telling you or reminding you about the prime number theorem, which says that the number of primes, so this is number of primes less than some real number x. This, I'm going to write this squiggly line, and so this is an asymptotic thing, and if you don't know what that means, then you can look it up. But this is asymptotic to x over ln x, which means that if I take this thing is often written as pi of x, which this pi doesn't mean 3.14, it's called the prime counting function. And so what this means really is that the limit as x goes to infinity of the prime counting function divided by that thing, x over ln x equals 1. That's what the asymptotic thing means. It means they're about the same size. It means this function grows about as fast as the prime counting function grows. And so what that means is if I want to tell how many prime numbers there are less than a certain number, then I can use this as a reasonable estimate in many contexts. Well, the ancient Greeks knew that there were an infinite number of prime numbers, and that's actually something that's quite easy to prove. The prime number theorem is not easy to prove. It actually took until 1896 for somebody to write out a proof of that. But the reason I chose this particular indeterminate form and with its infinite answer here is because it's related to a famous thing in number theory, the prime number theorem. If this answer wasn't infinity, then there wouldn't be an infinite number of prime numbers, and like the whole universe would fall apart or something. So anyway, now notice that if I apply this L'Hopital's rule, it seems to work, even though these conditions I wrote here are not satisfied, because I don't have the limits of the two functions here, the top function and the bottom function, both equaling 0. See, this was the 0 over 0 case that I wrote over here. This is a different case. This is infinity over infinity, which is why I wrote this here. Just to backtrack to compare to what we wrote before. You remember the way I got this 0 over 0 is I naively substituted in what would happen if I just put in a 0 for x and a 0 for x here. I would get a 0 over 0. Well, if I put in an infinity for x here and I put in an infinity for x here, I would get infinity over infinity. And so that's why I write this as the indeterminate form there in that case. But L'Hopital's rule appears to work, because see, watch what happens here. I would say limit as x goes to infinity. Now I would have d dx of x over d dx of ln x. And I'm going to write a question mark. Well, I shouldn't, because before that meant it wasn't valid, and here it is valid. I just haven't really explained to you why it's valid. I'm just showing you. So this is limit as x goes to infinity of 1 over, well, this is 1 over x. And so that flips over, and so this is limit as x goes to infinity of x, which is, of course, infinity. And, of course, for me to put a check mark here, you would say, well, I had better show you that it's actually true some other way, because I haven't proven that this way works. But I'm not going to, it's not too difficult to conclude or to see that this should be true. I mean, if you like, in this case, I don't mind if you just substitute it into your calculator and see that this gets bigger and bigger and bigger. The x grows much faster than the ln x does as x goes to infinity. I'm not going to go into any more details on that. But in any case, this does give the right answer. And so even though the form of L'Hopital's rule I've written here is just for the 0 over 0 case, that's the specific statement of it, it's actually more general than that. It will work if you have infinity over infinity, or it'll work if you have minus infinity over infinity, or if you have infinity over minus infinity too. Any of those forms work where you have a quotient where you have 0 over 0, infinity over infinity, or something like that. So it does work. Now, I'm not going to prove that. You know, the calculus book that we're using, you can actually go on their website and they have videos of proofs of these things. You probably won't remember. We wouldn't remember the proof if we went through it in detail anyhow, but I just want to show you that this does work in this particular case. Now, so we've seen example 2 now and saw how we could fairly easily get the answer with this same method. And then let's look at example 3. So now this looks a little bit different. This is the one where we have limit as x goes to infinity now, and then I have an x squared, and I have an e to the minus x. Now notice what's happening here. The x squared is getting big, so this gets big. The e to the minus x gets small. Notice down here I've written this thing, I've written a little square box around it on the board, is how can you tell when something's an indeterminate form or not? Because here I've written some expressions that have zeros and ones and infinities in them, and they're indeterminate forms. And then down here I've written some other expressions which are not indeterminate forms. Well, the way you can tell is if there are competing processes going on in the limit. What I mean by competing processes is that two things are pulling in different directions. Here, one thing's getting big, and so that makes the overall expression want to go to infinity. But here, something else is getting small, and that makes the overall expression want to go to 0. So which one wins? That's what it comes down to. So that's competing processes. Does the fact that this gets big make it go off to infinity? Or does the fact that this gets small make it go down to 0? Or do they balance each other out somehow and get something that's a finite, non-zero real number? Well, the way you can evaluate this is you can convert it into either this form or this form here. So watch what happens. I'm going to erase this. So to begin with, just to remind you, why have I written this as an indeterminate form? And I guess I've got this backwards, right? I wrote 0 times infinity, but the infinity really comes first here. So this is really infinity times 0, same difference. Why do I write that? Because if I substituted, so this would be the naive thing. So if I substitute, I would get limit as x goes, well, I'm not going to rewrite the limit, I guess. I would just substitute in infinity for the x there, and so I would get infinity squared. So a big number getting bigger, so that would be infinity times, and then I would get this e to the x, of course, or e to the minus x is 1 over e to the x. So this is 1 over some huge number there, 1 over infinity, which is 0. That's why I'm getting, that goes in for that. That's why I'm getting infinity times 0 here, this indeterminate form. And so you have those competing processes going on. So that's why it's written that way. But back to what I can do with this is I can write this as, I can either make it to be a 0 over 0, or I can make it to be an infinity over infinity. Now the way I would make it to be a 0 over 0 is I would write this as limit as x goes to infinity, and I would keep the e to the x here, or e to the minus x here, and I would write I would move the x squared down and take 1 over that. So I would, instead of multiplying by x squared, I would divide by 1 over x squared. And so now this looks like 0 over 0, right? Because that part goes to 0, this part goes to 0. That individual limit would go to 0, that individual limit would go to 0 here. And so I could apply L'Hopital's rule to this. Or I could write this, if I want to, I could do the other thing, and I could write this as limit as x goes to infinity. And I could leave the x squared alone. I could leave it up here, and I could move the e to the minus x down to the bottom and have that be an e to the x. And now this looks like infinity over infinity, because the x squared, the x squared gets big as the x gets big, so that gives me an infinity here. The e to the x gets big as the x gets big, and so that gives me an infinity there. Either one of these, I could write it as this, and then I could apply L'Hopital's rule. Now this one looks easier, because when I do the derivative, I just have to differentiate an x squared, whereas here I have to have a negative exponent, and that gets messier. So why don't I choose this one here? So what L'Hopital's rule would say then, so I'll just say apply, L'Hopital here. It would say that, and I'm going to leave this here, and there's room, so I'll just copy the whole thing. I'll just take an extra second longer. X squared e to the minus x dx. First I rewrite the limit this way. So this is limit x goes to infinity, x squared over e to the x. And then I can apply L'Hopital's rule. So I'm going to write LH here for L'Hopital over the equals sign here. So I have limit as x goes to infinity of, now I have 2x over e to the x. Because this is, the derivative of the top part was 2x, the derivative of the bottom part was just e to the x. Now I skipped a step here, and this is the last time I'm going to write this because it's a nuisance. The step was explicitly writing in the derivative signs, d dx, x squared over d dx e to the x. You know how to differentiate, so I'm just going to skip that now. We don't need to write that in there, so I'll just write what I have here, the 2x over e to the x. Well, this is still of the form infinity over infinity. And so what you're going to do here is you're going to do the same thing again. Now, I indicated this on the board here, this multiple use. That's why I put this down here. I was going to talk at some point about the fact that sometimes you have to apply L'Hopital's rule more than once in succession. You have to differentiate more than once. And this is an example in which case it happens. And so you're going to apply L'Hopital again. So this was L'Hopital applied number one time. This is applied the second time. And this will be the limit as x goes to infinity. And now this, I differentiate the top. I get a 2 over an e to the x here. That stays the same. And then this is no longer an indeterminate form. I can put in, the 2 is always constant. And so if I try to put in infinity for the e to the infinity here, it just gives me a 2 over infinity. And that's not indeterminate. It's a fixed number divided by something that gets bigger and bigger, and that goes to 0. So this limit here is just 0. And so, and that's kind of what you expect, because the polynomial here, and we'll see much more of this kind of reasoning, the polynomial here, the x squared, doesn't grow nearly as fast as what the exponential does. The exponential grows much faster. And so when I have the exponential in the denominator, that means that the denominator gets big much faster than what the numerator does. So the denominator dominates, and that makes the whole thing go to 0. And so that's why we get this 0 here. But notice what happened here. There were two important things that happened in this example that are worth paying attention to. The first is that we didn't have a form that we could immediately apply L'Hopital's rule to. We had this infinity times 0 thing instead. And we had to convert it to either this form or this form before we could apply the rule. It turned out this form was more convenient, so you have choices which one you could use. And then the other thing that happened, which was noteworthy, is that we had to apply the rule twice. We had to differentiate twice. And you have to be careful, because it can happen that if you try to apply the rule to something that doesn't satisfy the hypotheses correctly, then you'll get the wrong answer. So when you're applying it multiple times, you have to make sure at each step it still is an indeterminate form, this one and this one, that you can apply that rule to. Okay, so I want to look now at this example here, number 4, and show you how you would work out this one. So this is a famous limit, and it's one you should know. It's one you should have seen before. So this is, and this should go back to Calculus 1 again, or possibly Calculus 2, but probably Calculus 1. And so I'm telling you once again what the answer is, and this is e, and by e I mean the base of the natural logarithm. So this is 2.71828, and so on. So that's this limit here. Now, here again, you have this idea of competing processes, that one thing is getting smaller and one thing is getting bigger, and they're pulling in different directions. So as the x gets big, the 1 over x gets small. So the 1 plus 1 over x is getting smaller, it's going toward 1. So, this thing in here, the way that's looking is if I draw a graph and I draw a line across here at the height of 1, then this 1 plus 1 over x is going down like this. It's decreasing toward 1. However, at the same time, I'm taking this whole expression and I'm raising it to a bigger and bigger power. So that makes it want to get big. So I have numbers which, while the numbers themselves they're always bigger than 1, they're decreasing down toward 1, but I'm taking higher and higher powers of them. Now, the fact it's decreasing toward 1, that makes you think, well, maybe it goes to 1, the overall expression. But the fact that powers are getting bigger makes you think, well, maybe it goes to infinity. Which one of these processes wins? In this case, there's sort of a balance. The fact it comes out to something in between. It doesn't go to 1, the whole expression. It doesn't go to infinity. It goes to something in between, namely e. Now, to actually work this out, this requires a little bit more ingenuity. You have to apply some algebra to this before you can actually use L'Hopital's rule. So what you do is you use a sort of a trick. And this is a trick, I call it a trick, but it's something that you'll use repeatedly when you see an exponential like this. I guess I should have, what I was saying there is kind of, I'm saying this thing's getting close to 1, this thing's getting big. That's why I write this 1 to the infinity as the indeterminate form. Because if I just substituted the x in, going to infinity, this part would individually, the limit of that would be 1, and the limit of that would be infinity. And so you get this expression 1 to the infinity, which is shorthand for that particular type of indeterminate form. But the trick is to take the logarithm of this thing. And so what I'm going to do is I'm going to start by writing y as a function of x. And y is going to be this expression here, 1 plus 1 over x raised to the x power. And then so the natural log of y, I'm going to leave off the of x here just because it gets messy. ln of y is just x times ln of 1 plus 1 over x. Now I can write this as ln of 1 plus 1 over x over 1 over x. See, I've taken the x and I've moved it down to the denominator. Now, why have I done that? Well, the reason why is because, so let me just sketch for you. Remember how the log function looks. The log function looks like this. So this is the value, this is where x equals 1. I guess I won't say x, I'll just put the value of 1 here. This is where it crosses the axis. So this is where the value is 0. And then here it's going down to negative infinity, and here it's going up to positive infinity, the values. That's what the ln function looks like. So as the 1 over x gets, as the x gets big, the 1 over x will get small. So this will get close to 1 inside here, and the ln1 will get close to 0. And so this is going to look like a 0 there. And then the 1 over x, as the x gets big, the 1 over x will get small, and this will look like a 0. So the whole point of this strategy, going from here to this step, is to eventually get an indeterminate form that looks like 0 over 0. So that's why I did that. Now let me erase this here, and erase this here. And then so I've written ln y is this. And now what I'm going to do is I'm going to look at the limit as x goes to infinity of ln y. And of course this is this limit I've written here. And I'm going to run out of room, but let me scoot this down a little bit so I have room. Let me move it over, I guess. So limit as x goes to infinity of ln y equals limit as x goes to infinity of what I just wrote there, ln 1 plus 1 over x over 1 over x. And this is exactly the indeterminate form that I wrote up here. This is 0 over 0. So I can apply L'Hopital's rule. Okay, well, let's do that. If I differentiate the numerator here, I'll get, now this is going to look a little messy, so don't get upset, but it's, so I have to apply the chain rule. I have ln of something, and so when I apply the chain rule, I'll tell you what, let me scoot this up here just a little bit so it will fit better. I apply the chain rule, so I'm going to get 1 over this whole thing, 1 plus 1 over x. That's this whole thing inside here. Notice I haven't done anything with the denominator yet. And then I have to, so all I've done so far is I've taken the ln 1 over x, I've taken 1 over that, and then I have to take the derivative of the inside, and the derivative of the inside is derivative of, so this would be d dx of 1 plus 1 over x. Well, the 1 dies, the d dx kills it. The 1 over x, this is just going to give me minus 1 over x squared. So I've pulled out this, I have 1 over this thing, and then I have to multiply this whole thing by 1 over, so I have a minus 1 over x squared here. And then what I have in the denominator, so all this is in the denominator now, this whole thing up here, that was just the derivative of this part here. The derivative of this part, well, I just did it. It's nothing but minus 1 over x squared. This is in the denominator, this is in the numerator, these things cancel. And so I'm going to get, let me write it up here so I have room for one more line. This is limit as x goes to infinity of 1 over 1 plus 1 over x. Now, at this point, this is no longer an indeterminate form. Why? Well, I have the 1 here. The limit of that is just 1 always. I have the 1 plus here, and then I have the x going to infinity. The 1 over x is going to 0, so this is just 1 over 1, and so this equals 1. Well, it doesn't equal e, but I don't expect it to equal e because I'm looking at the logarithm of this expression here. I'm not looking at this expression itself. Okay, so what I've gotten is, now you can always rewind this. So I'm going to erase the part below this line here because we've come to the conclusion that we need to come to for this part here. And so that was kind of all the commentary. So what I worked out, so I defined y of x to be this. And then I worked out the limit as x goes to infinity of ln of y of x is equal to 1. Now, suppose I could do this. So I'm going to write equal sign, I'm going to write a question mark above it. And this will turn out to be valid. You know, before my question mark meant that it was invalid. This will actually turn out to be valid. This will turn out to work, but it's not obvious that it works. Suppose I can pull the ln outside of the limit here. So suppose I could write ln, that this equals ln of the limit of, as x goes to infinity, of y of x. Well, I'll tell you what, rather than pull this out like this with the equal sign, what I'll say is, can I do this? Can I do this, where I interchange the order of the ln and the limit there. I push the limit inside the ln, and over on this side I would still have the 1. And then I would take, so there would be a question mark here. Then I would exponentiate both sides. And so I would take e to the ln of this equals e to the 1. And of course, you know that e to the ln of anything is just that thing. So this would say limit as x goes to infinity of y of x equals, and you know e to the 1 is just e. But y of x was my expression that I started out with originally. That was what I wanted to show. So when I just substitute back in what y is, so this would say limit as x. So this would say limit as x goes to infinity of my special little friendly function here. And that's equal to e, and that would be what I would want. Now, it all hinges on whether I can change the order of whether I can move the ln outside of the limit. And the answer, so when I say, can I do this, the answer is going to be yes. And the reason why is going to be because ln is a continuous function. So there's a theorem here that if you have a continuous function, you can do that. So ln is a continuous function. Now you might think that that's a nuisance, and of course this was the answer that we wanted to get. You might think that, well, how would I remember that? And you don't really have to. I mean, most all the functions we're going to deal with are not only going to be continuous, they're going to be differentiable. Not only will they be differentiable, they will mostly be infinitely many times differentiable at any given point. There will be a few exceptions, you know, places where there are singularities or something, but mostly we'll be dealing with functions like that. Okay, so let's just briefly evaluate where we are at before we go on a little further. And so where we are at is we have, So what have we done? Well, we've seen how to apply this nice little bit of technology we have here, L'Hopital's rule, to 4 types of indeterminate forms. And it's taken a while to get there. And because that's true, I want to just show you, just briefly, you know, if you start to recap this, you'll see it's not nearly as complicated as it seemed to be when we were actually working it out, because there was all kinds of commentary. And of course, if we were doing this in class, people would be asking questions and it would stretch out. And so so, you know, when we looked at number 1, the way we would do this, once we know what to do, is we would just write the following. Watch how fast this is. Limit as x goes to 0 of sine x over x equals limit as x goes to 0 of cosine x over 1 equals limit as x goes to 0 of cosine x equals 1. So that was number 1 done. Number 2, I would say just limit as x goes to infinity of x over ln x equals limit as x goes to infinity of 1 over x equals infinity. So that was 2. And then 3, well, I remember I just converted. I'd say limit as x goes to infinity of x squared e to the negative x equals limit as x goes to infinity of x squared over e to the x equals limit as x goes to infinity. Remember, this is the one where we had to do it twice. 2x over e to the x equals limit as x goes to infinity of 2 over e to the x equals 0. And then the fourth one was a little bit more complicated, because we did this substitution where we said y equals this thing, and then we took the natural log of it and so on. But I just want to impress on you that once you know what to do, once you know how to apply this rule, you can crank through these things very quickly. It's just, you know, a few seconds actually for each one of these. Okay, so that's what we've done. Now, what we haven't done is we haven't talked about when L'Hopital's rule works and when it doesn't work. And it's, I mean, so I'll show you an example. So here's an example of so this is an example of when L'Hopital's rule fails. And this is going to be very simple. Suppose I have the limit as x goes to 1 of x over 1. Well, obviously that's 1. You know that, and you can tell that just by substitution. But suppose I try, suppose I try L'Hopital. What I would get is I would get the wrong answer. Limit as x goes to 1 of x over 1 equals, well, I would try to differentiate the limit as x goes to 1 d, well, I don't need to write out the d dx and all that. I differentiate the x, I get the 1. I differentiate the 1, I get 0. And so this would look like, is that equal to infinity? What went wrong? Well, what went wrong is the hypotheses of L'Hopital's rule that have to be true before you can apply it aren't true in this particular example. So let's talk about what these hypotheses are really quickly. So I've written them out there, and you've been able to stare at them for the last however long it's been. let's talk about these in a little bit more detail. So this is L'Hopital's rule in the case where 0 equals 0, or where we have 0 over 0, this indeterminate form. And so we have some interval. So this applies when you have some interval, so this is an open interval, and I call the left endpoint A, the right endpoint B. And inside that interval somewhere is another point C. And this is the point at which the limit is. Now in this particular case, what I have is I have some function f of x. And this is going around, and it's that doesn't even look like a function, does it? Let me write this over here. So this is f of x, and this. So it somehow looks like the limit there is 0 or something. And then maybe I have some other function g of x here. And this is kind of going through, and it also has a limit of 0. That's what this condition here is saying. So I have this kind of picture. Okay, so let's look at it. We have an interval. We have two functions, f of x and g of x. Now I'm going to assume that f of x and g of x are differentiable, their derivatives exist on this entire interval, except it doesn't have to be true that the derivatives exist at that point C, where you're evaluating this limit. And so this notation here, where I've drawn the interval notation and I put a minus sign and I put the little brace with the C, this is a set notation for C. It's the singleton set that has just one element in it for C. And so all this means is essentially that I take that open interval from starting at A and going to B, and I just draw a hole there, C. So that's what this expression, AB minus the singleton set C is. That's what it means. So when I write here that f and g are both differentiable on the interval except for at that point. Now they may be differentiable at that point, it's just that we don't care whether they are or not. They just have to be differentiable everywhere else in the interval, and they may or may not be differentiable at C. And then it also has to be true that the derivative of g is not allowed to be 0 inside that interval here. And I guess my picture I drew here wasn't good enough, because you see here inside that interval here, g of x does have a place where the derivative, well, two places actually, where the derivative is 0, where the slope is 0. So let me draw g to where it doesn't do that. So now my g here will work. And this is because you don't want division by 0, because when you're doing the derivative here, you don't want to have division by 0. Okay, so you have f and g are differentiable on that interval except for at the point C, possibly. The derivative of g is non-zero on the interval except at that point C. Now you might say, well, why should what g does over here, when this had like a horizontal tangent line here where the derivatives are 0, why should it affect what happens here? And it really doesn't. The point is you can make the interval a be as small as you want, but I won't go into those details. So I have f and g differentiable on that interval, possibly except at that point C. The derivative of g is non-zero on that interval except possibly at C. And then the limits of the individual functions f and g are both 0 as you're approaching C. And so that's why I've drawn these crossing at 0 here. Now it doesn't say the function values are 0, it just says the limits are 0. So I could have, for instance, I could have a hole here, and then I could have a f of 0 here and a g of 0 down here or something. But anyway, so now the fact that this is giving me 0 here for both these limits, this limit is 0 and this limit is 0, that's why it's the indeterminate form 0 over 0. And we've already seen this many times, the idea that when you just naively substitute in for the function values that I'm getting 0 over 0. So that's why I'm saying this is L'Hopital's rule in the case where it's in indeterminate form 0 over 0. Now if all those conditions are true, then you can just take the derivative of the top and the derivative of the bottom and divide by those two. And this is what we've been doing. We've been starting with the limit of the functions. I mean, like the first one that we did, where we had limit as x goes to 0, sine x over x. What we did, so in this case, the sine x was the f of x. The x was the g of x. And when we wrote that this is equal to the limit as x goes to 0 of cosine x over 1, then the cosine x is just the f prime of x. The 1 is just the g prime of x. And so this is a conclusion that you can draw. Now this is the case if the right-hand side, if the limit over here, if the limit of the quotient of the derivatives, if it exists. Now something that might happen that we saw, and we saw it with this case where we had x squared over e to the x. That was what came out of this example here. It may be that you have to do it again, because it may be that this limit here gives you an indeterminate form. And then you have to do it again. And you might have to do it again and again and again. I mean, for example, if this was an x to the 5th, you'd have to do it 5 times, because the e to the x will always keep on giving you the same e to the x back. It'll never simplify any. Okay, so these are the hypotheses. And so what went wrong in this example where I was looking at limit as x goes to 1 of, what was it, 1? Oh no, it was x over 1, I guess. No, it was 1, I think it was 1 over x. Can't remember. So, and what I wrote, so I wrote the question mark here. If we try to apply L'Hopital's rule, no, it was the other way around. That's right. It was x over 1. If we try to apply L'Hopital's rule, x goes to 1 here, and then we get a 1 over 0, and we get the wrong answer, you know, and we get the wrong answer here. What was wrong with this? Well, in particular, the 1 here, that was a constant function. And so the hypothesis that the limit of g of x has to be equal to 0 wasn't satisfied. See, this thing wasn't an indeterminate form to begin with. This didn't look like 0 over 0. This looked like 1 over 1. And so it looks like 1 over 1. You can just substitute in that particular case. Now, what this is telling you is not only that you don't need L'Hopital's rule if you don't have an indeterminate form, but it tells you that if you don't have an indeterminate form and you try to apply L'Hopital's rule, you will often get the wrong answer. So it's not just that it's unnecessary, it's that it's incorrect to apply L'Hopital's rule unless these conditions here are satisfied. Okay, so where are we at? Well, there's one more expression that's written on here that we didn't talk about, and I'm not going to work this out in detail. I just wanted to include this as motivation to kind of show you an application of this kind of thing. I wrote this crazy limit here. I wrote crazy, and then I wrote this limit here. And you see this expression here that looks kind of like the 1 plus 1 over x, except there's a minus here. That's raised to the x. And then it gets even crazier because you've got that whole thing raised to x, which itself is raised to some other power. And so I've written this gamma here, x to the gamma. Where does this limit come from? Well, interestingly enough, I encountered this limit in the context of a research program about physics. And what this, the context in which this arises is, so the way the crazy limit this crazy limit shows up in the context of cosmology. So this is the cosmology of the early universe. So this is so this is essentially well, there was supposedly this phase in the early part of the universe which is called the inflationary epoch, which is where space-time expanded very rapidly over a short period of time. And some people, myself included, think that that's not a very good explanation. And so in attempting to come to a better explanation, I had to work out a particular probability distribution, and it had this limit in it. And so this is a 1 to the infinity sort of thing. So it's an indeterminate form. And it turns out that depending on what the value of the gamma is here, that this will give you one of several. There's like 3 different values that it could give you. And the fact that there's this one particular value shows that that model essentially gives you something that could mimic what the inflationary idea is supposed to give you. So anyway, I mean, that's, I haven't really explained it. I just wanted to impress upon you that this is not just totally random stuff, that there are things that you use this thing for. And that just a month or 2 ago, I actually encountered a particular case in which I had a limit that looked like this. Now, it was a little bit wilder than any of the limits that show up here, but it was still essentially the same type of thing going on. Okay, so I hope that that gives you at least some idea of what indeterminate forms are, why we care about them, and how we can tackle them. There are a few others, like I said, infinity minus infinity and so on. And there are many other expressions you can write that have zeros and infinities and ones in them that are not indeterminate forms, like what I've written here. The thing to remember is it's indeterminate when there's some kind of competing process where one process wants to make the limit go to a large value, one wants to make it go to a small value or something like that, and you can't tell just by plugging things in which one of those 2 processes wins. But I think this should tell us what we need to know for the introduction.